Welcome back to Alien Professor. Today we're tackling a problem that sounds simple but is brutally deep. What is the universe doing? And are we interpreting what we see correctly?
Translation: humans looked at the sky, did math, felt confident, and now the universe is like, cute.
We'll cover three things: what JWST is actually seeing in the early universe, why that creates tension with the standard model, and why some scientists are exploring alternatives like timescape cosmology, where time itself could create an illusion of acceleration.
So is this the episode where you tell everyone Einstein was wrong?
No, it's the episode where we explain what's solid, what's uncertain, and why scientists argue about the uncertain parts.
Okay, Professor. Explain JWST like I'm a confused alien, which I am.
JWST mainly observes infrared light. That matters because the universe is expanding, so light from very distant galaxies gets stretched to longer wavelengths. What started as ultraviolet or visible light arrives at us as infrared. JWST is designed to detect that faint red-shifted light. Its mirrors are cooled to around 7 Kelvin for extreme infrared sensitivity.
So it's basically a time machine that sees the universe in stretched colors?
Exactly. But here's the crucial part. JWST does not directly see the past like a movie. It measures light. Then we infer distances, ages, masses, and temperatures using models. Those inferences can be very good, but they depend on assumptions.
Humans, the species that builds a telescope and then argues about the interpretation for 10 years?
That's called science. And JWST has provided a lot of data that is forcing us to test whether our assumptions hold up in the early universe.
You keep saying standard model. I know humans love standards, like standard chaos. What is it?
In cosmology, the standard model is often called lambda CDM. CDM means cold dark matter, the invisible matter that provides extra gravity needed to form galaxies. Lambda is the cosmological constant, a simple form of dark energy that makes the expansion of the universe accelerate.
So the universe is made of normal stuff, invisible gravity stuff, and invisible pushy stuff.
Yes, roughly speaking, about 5% is normal matter, about 25% is dark matter, and about 70% is dark energy. Those numbers come from many independent observations, especially the cosmic microwave background, galaxy clustering, and supernova measurements.
And you feel good about this?
We feel good about how well it fits a huge amount of data. But fitting data is not the same as fully understanding the underlying physics. Dark matter and dark energy are still not directly identified in the lab.
Now tell me why JWST keeps giving scientists headaches.
One major tension is that JWST is finding galaxies in the early universe that appear more massive, brighter, and more chemically evolved than some simulations expected. In the standard model, structure formation is hierarchical. Small clumps form first, then merge into larger galaxies. That takes time. Many initial two massive galaxy estimates from photometry were revised downward after spectroscopy, like in the CEERS survey from 2023 to 2024. But JWST data from programs like Cosmos Webb and FANGS still indicate higher early star formation efficiency.
But JWST shows big adult galaxies showing up early, with a mortgage and lower back pain.
Some of the surprise may come from how we estimate masses. We infer stellar mass from the galaxy's brightness and color, but dust, bursts of star formation, and the presence of active black holes can bias those estimates. Early JWST results were sometimes revised after better spectroscopy.
So the universe might not be breaking rules. Humans might be misreading the scoreboard.
Possibly. But even with revisions, JWST still pushes us to refine models of early star formation, feedback, and black hole growth. The core point is not everything is wrong. It's that the early universe might be more efficient at building structure than we assumed.
Let's talk expansion. Why does everything look like it's running away from us?
We observe redshift. Light from galaxies is stretched. The simplest interpretation is that space expands, increasing distances between galaxies. Edwin Hubble discovered the relationship between distance and recession speed. The farther a galaxy is, the larger its redshift.
And you're sure it's expansion, not galaxies all agreeing to leave at the same time?
Expansion explains the pattern elegantly. But here is where things get interesting. There are different ways to measure the expansion rate today, called the Hubble constant. One method uses the early universe, especially the cosmic microwave background. Another uses the late universe, like supernova and Cepheid stars. These methods disagree beyond what we expect from measurement error.
So the universe has two different speeds depending on which part of the universe you ask? That's suspicious.
That disagreement is called the Hubble tension. It could mean unknown systematics, or it could mean new physics, such as early dark energy, evolving dark energy, or something else in the cosmic model.
Dark energy time. Explain it without waving your hands too much.
We infer dark energy because supernova data and other measurements suggest that expansion is accelerating over cosmic time. In general relativity, accelerated expansion requires something like a negative pressure component, which can be represented by a cosmological constant, lambda.
Negative pressure. That sounds like the universe is socially distancing.
The cosmological constant is mathematically simple and fits many datasets, but it creates a deep theoretical puzzle. Quantum field theory predicts vacuum energy values that are absurdly larger than what cosmology measures. That mismatch is often called the cosmological constant problem. It is one of the biggest unsolved problems in physics.
So the universe either has tiny vacuum energy or humans don't understand vacuum energy. Both are embarrassing.
Exactly. And some newer analyses hint that the strength of dark energy might not be perfectly constant. If dark energy evolves, we would see subtle changes in how expansion history behaves. That is under active research and debate.
Explain something that drives humans insane. If space expands, why doesn't my head expand?
Because on small scales, other forces dominate. Gravity holds solar systems and galaxies together. Electromagnetism holds atoms together. Expansion is extremely weak locally compared to those binding forces. The standard picture treats cosmic expansion as a large-scale behavior of the metric, while local systems are effectively decoupled.
So the universe expands where it's lonely.
That's a poetic summary. Expansion is most relevant where matter is sparse and gravity isn't strongly binding structures.
Okay, now give me the weird one. The time illusion theory.
Timescape Cosmology is an alternative framework proposed by David Wiltshire to explain apparent acceleration without dark energy. It focuses on the universe being lumpy on large scales. We have dense regions like galaxy clusters and vast underdense regions called cosmic voids. In general relativity, gravity affects time. Clocks tick differently depending on gravitational potential and the distribution of matter. Recent tests with DESI 2024 data still favor lambda CDM over timescape.
So void clocks are speed demons and galaxy clocks are stuck in traffic.
In the timescape picture, because voids are underdense, they effectively expand faster. Over billions of years, voids come to dominate the volume of the universe. If you average observations across regions with different clock rates and different expansion histories, you can produce an apparent acceleration in the average data. The claim is that what looks like dark energy might emerge from how we average time and geometry.
So the universe is not accelerating. Humans are just doing cosmic accounting wrong.
That's the argument. But there are major challenges. The model must match the cosmic microwave background, baryon acoustic oscillations, gravitational lensing, and structure growth simultaneously. Lambda CDM still performs extremely well across many datasets. Timescape is interesting, but not mainstream.
So can we put Einstein was wrong in the thumbnail? It gets clicks.
You can put it in a thumbnail if you want drama, but scientifically it would be misleading. General relativity continues to be confirmed in many regimes. The issue is whether our cosmological model, which uses relativity plus assumptions like large-scale uniformity and a specific form of dark energy, is complete.
So the honest version is Einstein was right. Humans may be oversimplifying the universe. Less clicky, more true.
Exactly. Science is not about humiliating old theories. It's about refining models as evidence improves.
Final answer. Is the universe expanding, or is it just doing a really convincing magic trick?
Expansion is strongly supported by multiple lines of evidence. The big open questions are about details. The exact expansion history, the nature of dark energy, the Hubble tension, and how early structures formed. JWST is not breaking physics. It is giving us higher resolution evidence that forces stronger tests.
So the universe isn't falling apart? Humans are just upgrading their confusion to 4K.
That might be the most accurate summary you've ever said.
Like and subscribe. There's a new episode every Sunday. And trust me, reality still has plenty of surprises left.
And if you want more episodes where we separate real science from sensational headlines, you are very welcome here.